Cisco Certified Network Associate Day 44. Welcome back everyone, I'm Imran, your trainer for this entire series. Today we start OSPF routing, and this with EIGRP is one of the most sought after topics in this entire series. So without wasting much time, let's get straight into today's class. Before we go anywhere, click on that subscribe button and click on the bell icon to be notified when we add a new video. Also, don't forget to click on that like button under this video, which would make us really happy, and then it would help us rank higher and more people would get benefited. You would find our social media contacts on this page. On the left, my company social media contacts, and on the right, my personal social media. And for people who want my email address, that's imran.rafai@nwking.org. So what are we going to look at in this video? Today, we're going to look at 2.4. Now, 2.4 says configure, verify and troubleshoot single area and multi-area OSPF version 2 for IP version 4, excluding authentication, filtering, manual summarization, redistribution, stub, virtual link, and LSCs. So this is not going to delve too much into OSPF. It would introduce you to OSPF to show how to configure OSPF, and that's about it. But since this is a configure topic, I'm going to take it in two videos, at least two, maybe three. In this first video, it's going to be theoretical. I'm going to show you and explain to you the theory of OSPF and how OSPF works. In the next video, we will get into the configuration mode. So we will start packet tracer and we will configure OSPF, right? So what are we going to look at in this video? We're going to look at three things. The first one, what is OSPF? Second, we will look at OSPF, the process and how OSPF works. And then the third thing we're going to discuss is OSPF areas. What is OSPF? Like discussed in the last video, OSPF is a link state routing protocol compared to RIP, which is a distance vector routing protocol. Now, in a link state routing protocol, the link between the networks, or rather the link between routers, are important, and routing decisions are made depending on the speed of the link, right? So if you have a higher bandwidth link, that link is going to get more priority than a lower bandwidth link, which could be much shorter. So if it's distance vector, like in RIP, like we discussed last time, if it is one hop, RIP would choose that immediately over there. It is the slowest bandwidth connection that's between them. But in OSPF, even if it has to hop two routers to reach to a certain network, it would choose that if that network or that route is using high-speed connections. We'll look at it in a little while in this video. But for now, you understand link state routing protocol looks at the link state. Now, OSPF as a routing protocol was developed in the year 1988. Now, it was an open standard. That means every manufacturer could technically use OSPF, and OSPF was used by a lot of providers, and that is why it is one of the most used routing protocol, or rather IGP, interior gateway routing protocols. OSPF also had with OSPF version 2 that supports only IP version 4, right? It supports only IP version 4. So at about the same time, they developed OSPF v3 for IPv6, right? So IP version 6 is supported in OSPF v3. So though it was like released in 1989, it took a while for it to start being used. So it was by 2008 when it released few more technical capabilities to OSPF v3, and they released in 2008, right? So major RFCs that went through to get OSPF to widespread use were released in 1989, and then there was another RFC in 2008. Why OSPF? Right? We discussed a little bit in the last video. OSPF is much faster, right? The convergence is much faster than RIP. Most of the time it's less than 1 second, and I will tell you how to increase the convergence speed right? When we discuss a little while later. But just know OSPF is much faster than RIP. OSPF, it is an IGP, we discussed that. It is classless. Now, if you remember, RIP is class full. So even if you had like a CIDR notation of, let's say, class A IP address, if you're doing class A IP address /24, it wouldn't accept that. It would consider, if you type an IP address of 10.1.1.0 /24, it would just consider it as a 10.0.0.0 network because it considers the whole network. So it's class full, at least version 1, but OSPF is classless. It has also got authentication. So you could have, if two routers need to do share OSPF information, we could set up an authentication where only if it authenticates the password, would it become neighbors, and only then would it start sharing information, right? So authentication is also supported, and like we discussed, it is open standard, and so a lot of manufacturers use OSPF. Now, on a broad level, if at all you look at it from like a high level, an eagle eye view, OSPF basically works by sharing LSA, nothing but Link State Advertisements, right? Link State Advertisements. Now, what does the LSA have? An LSA, basically, an LSA is generated by a router, right? That's called LSA type 1. So we're not worried about the LSA types, but just know LSA is generated by the router. It's called a router LSA. Now, LSA contains a lot of information. Primary is the router ID, the router ID of the router that generates the LSA. It contains the network that it knows, right? Then it talks about the cost. So there are a few information that you need. Now that's all in LSA. Now LSAs, they keep sharing LSA. So router 3 would send an LSA to router 5, router 5 would send an LSA to router 3, right? These LSAs are nothing but data structures, like we discussed, and they stay in something called as a link state database, LSDB, right? So they collect all these LSAs that they receive and they put it into a database, right? So ideally, what happens is once they form neighbor, now before they start sharing LSAs, they need to form neighbors. So neighbor is formed by sharing hello messages. Now we'll look at all that in a while, but just know what happens is once they get a link state database formed, now router 3 and router 5 will start comparing LSA database, right? So it would say, okay, it would send a message called database description, right? DBD. This is a database description packet. It sends that packet to router 5, and they both, in fact, both of them send each other a DBD packet. Once they get the DBD, what DBD tells is it just gives them an overview or an index of what LSAs that they have. Now, if they compare, now router 3 and router 5, they compare, router 3 would receive DBD from router 5 and say, okay, I have 3, 4, and 9. So just send me 5 and 7, right? So it would, router 3 would send an LSR, link state request, LSR, to router 5 to send 5 and 7. Similarly, router 5 would say, I know these three information, so just give me 1 and 2. So it would send an LSR for 1 and 2. Now, once link state request comes, what it does is it sends an LSU packet back, right? LSU, link state update. So if R3 requests LSR, R5 would send an LSU, link state update, right? So this is how they update each other. And once that's done, after they do whatever the exchange that they need to do, you have a state where like in this case, both these devices, but if you have 10 routers, all the 10 routers would have the exact same LSDB, right? This is how OSPF starts calculating its route. So once it has an LSDB, it has all the information that it needs. So it knows the entire network, right? It knows the entire network of OSPF devices. And then once you have all the information and all the links that's connected between these devices, OSPF uses something called Dijkstra's shortest path first algorithm. It's a very old algorithm. Now it uses that algorithm to generate the routing table, right? So very important stage is to have this LSDB synchronized across all devices in the network, right? So like I said, once this happens, every device in this network, like for instance, in this case, there are 8 routers, and each of those routers exchange link state request and link state update. And before that, of course, they have to form a neighborship. We will talk about neighborship and how this process of request and update happens. But just for now, understand that each of these devices, at least if it's like a point-to-point network, right? If it's a point-to-point network, each of these devices would share updates with each other, and they would have the same LSDB. So if all the LSDB states are updated, if everybody has the same LSDB, they can start each of them. Like for instance, router A can have Dijkstra's SPF algorithm running and generate a routing table. So it generates a routing table for itself. That routing table will not be the same for router 3. Router 3 would have its own routing table using the same database, but it is calculating the routing table from his perspective, right? From router 3's perspective, how to reach each of those devices. Similarly, router A would do from their perspective, right? So to do that SPF algorithm, they need to have the LSDB updated, right? So how does OSPF work? Like we discussed, OSPF needs to do 3 things. First, it needs to form a neighbor. Second, it needs to update LSDB, right? Build and update the LSDB. And third is to build the routing protocol. Now, technically, if you see, as an administrator, this is the only step that we really need to fine tune, right? So we could do some control. Maybe like manually we can configure the router ID, right? Or we could manually change the timers, or maybe if you're configuring the OSPF networks, you don't give the wildcard mask. Now in this case, OSPF, we will look at it, how to configure the device, configure OSPF in the next video, but OSPF uses wildcard masks. So if your wildcard masks are not matching, if your subnets are not matching, if your authentications are not matching, neighborship will not form. So one of the major things in OSPF troubleshooting that you would be doing is to check why neighborship is not forming. So if neighborship is not forming, you need to know what are the parameters that need to match for the neighborship to form, right? So that's where you should concentrate. Building LSDB, you are not really doing anything as an administrator. Once the neighbors are formed, the LSDB gets updated by itself. Routing table gets updated by itself, right? This is all done by the OSPF device, right? You as an administrator is going to be bothered about neighborship. If neighborship is not forming, there's something that is wrong and you need to troubleshoot. So let's take an example. Let's take 2 devices, and for simplification, I have given a router ID of 1111 and this 22222, right? Let's connect a link between the 2 devices. Once the link comes up, it says, okay, the link is up, right? And let's assume that OSPF is configured on both these devices. So I've just gone there and manually typed the OSPF command and then route OSPF, and then I've given all that. Don't worry, we will do the configuration bit, like I said, in the next video. But let's assume OSPF configuration part is done and I've connected the 2 devices. Immediately as soon as link comes up, router A would send a hello packet, right? It sends a hello packet, and in the hello packet, of course, it'll list all the information saying the router ID, it'll tell whatever networks, let's say whatever network it has here, it'll list that, and it will say that I've not seen any router. So basically, it has not got any hello packet before this. So it's saying I have not seen any anybody in this link, right? I haven't seen anybody in this link, but I am 1.1.1, right? It tells itself, it introduces itself, and router B receives that. And when he receives a hello packet, router B says, okay, I can see that there is a OSPF, a potential neighbor candidate in this link, right? So I'm going to go into something called as the init state, right? He's going to be in an init state and he receives that packet. Now, where does it come? This hello packet does not come to router B. It's not like it is not a unicast communication. It is not even a broadcast communication. hello packet go into a multicast IP address. So it sends to 224.0.05. That's the multicast IP address of OSPF. This is where router A will send. Now what happens is, like, when you're talking about multicast, now a lot of people ask this question, what's the subnet mask for multicast? There's no subnet mask for multicast. Multicast is like a radio signal, right? You have a radio signal and you know 91.0, FM 91.0 is the radio station. What do? You go to your radio, right? Or whatever, let's assume this is the old radio. So you have a radio at home and you tune your device to 91.0, right? And then you receive the signal. So similarly, multicast is like that. Router A sends 224.0.0.5. This multicast address it sends. Router B, since it's also configured for OSPF, it listens to this multicast address. When it listens, it hears that router A has sent a hello packet, right? When it receives that hello packet, like I said, it goes into init state and it sends back. Before we do that, these are the things. When you look at hello packets, for neighbors to form, like if they have to form a neighborship, the hello and dead interval needs to match. So if at all you've gone into router A and you configured the hello packet timer to something else other than the default value is 10, if you configured it to 30 or 50 or whatever number, and if router B has not matched that value, they will not form, right? So this is critical. You need to match this value. Authentication should match. So if both of them are doing authentication, it should be the same authentication type that they're doing. And of course, the authentication password also should match. Area ID, of course, that should match. If one is doing in area 0 and area 1, that will be difficult. What is area? Now, wait for few slides. We will talk about area in a while, but just know that area ID should match. The prefix length should also match. That means if one side you're saying it is /24, the other side also should be /24, right? So here, another thing you need to be critical, which we will discuss in the next video. It is not subnet mask. They use wildcard mask, right? And you know what wildcard mask is. So that's something we would be using. And of course, stub area flag should also match. So these are the factors that should match for a neighbor to form, right? So once this happens, router B sends a reply hello packet. Basically, it sends a hello packet. But the only thing is it says that it has already seen 1.1.1.1 in this medium, right? So in this interface, on this medium, it has seen 1.1.1. That's another OSPF candidate that is there on this, and I am 2.2.2. So when router A receives that and says, okay, I see that he's sending me a hello, but I also see that he's seen me already. That means I am already in two-way, right? I sent a hello, I received a hello. Now when this happens, router A, what it does, it sends its own hello, but this time it says, I've already seen you and I've already seen myself, as in I sent, you saw me and you said you're there and I've sent, right? Basically it says I've seen 1.1.1 and 2.2.2 and it says I'm 1.1.1. So now router B says fine. Now I have sent a hello packet, he's seen me and he's sent me a hello back. That means I'm also in two-way. So both of them go into two-way. Now this is a very critical stage because in this case, it is point-to-point because it's a serial connection. But what if we use, let's say we have a switch, right? And we use a shared medium, right? If there's a shared medium, it will not, most of the device here will not go beyond the stage. Everybody would be in this stage. Among these four devices in a shared medium, one of them would be a designated router, DR, and another router would be a backup designated router. Now what happens is each of these devices would form a full connection. Now what is full connection we will see in a while, but it will form full connection only with the DR and BDR. With the other non-BDR device, or basically they say DR other device, it would stay at this. So this particular router, in this case, let's call it C and D. C and D will only stay at two-way. It will not go beyond two-way. It would always, if you go to see and look at IP, show IP OSPF neighbor, it will say that it's in full neighborship with DR and BDR, but with the other router, it is in a two-way state, right? So two-way state is very critical because that's where it will be. And at this point, basically what it said is when they go to two-way, another thing that is critical, like if you're doing troubleshooting, you need to know that if they've reached two-way, that means all these parameters in your hello packet have matched. So there's no problem. Everything is matched and they're ready to be neighbors, right? So this is the two-way state. So once two-way state happens, they send a packet. Now we discussed this. It's called a database description packet. Router A would send a database description packet and the state would be in X start, exchange start. What is database description? It is like an index sheet, right? On your, if you read a book, there's an index sheet. It gives you everything that's there in that book, right? So similarly, a database description is more like an index for the Link State database of that device, right? So router B also does the same thing. It sends a database description and it goes to an exchange state, right? One is an exchange start, the other one is an exchange. So both of them are basically doing is sending a database description packet to each other. Once that happens, we discuss this link state request, link state update, and link state acknowledgement, right? This is acknowledgement, LSA, but LS acknowledgement basically. So depending on how many LSAs that they have to exchange, it would send a link state request. Then the other device would send a link state update back, and the first device would send a link state acknowledgement saying, I have received it, right? And this goes on for as many times as they want the LSA exchange. So once all the LSAs are exchanged, they go into a state known as full, right? And also once this exchange is happening, they would stay in a loading state. So if you see loading, that means that LSAs are still being exchanged. The LS database has not been updated, right? So once all that exchange has happened, they go into a full adjacency state called as full. So once you see they are in full, that means they are in full adjacency state. Like we discussed, this full state would be achieved in a shared medium. Now this is point-to-point, so there's no other device point-to-point generally between two devices. If it's a shared medium like an Ethernet, only full adjacency would happen only with DR and BDR. The device which is not a BDR or DR would only have two-way neighborship, right? So how is DR and BDR elected? Now that's an important question. So let's say in a shared medium, okay, how does DR election happen? DR election basically first thing they do is they look at OSPF priority, right? Second thing is router ID. Okay, so if OSPF priority is highest, whoever is highest, that will become the DR. If OSPF priority matches, like if it's a tie, then they would look at highest router ID. Who has got the router ID, highest router ID, they would become the DR. Similarly, another BDR, right, a backup designated router is elected, and they would be a backup designated router. Now, if the DR were to die for some reason, immediately the BDR would become DR and another BDR would be elected, right? This is very critical. Now I didn't make a slide for that because it just slipped my mind and I just realized it when I was doing, and now I don't want to pause this and create a new slide and then come back and just delay the whole video. So I hope you understood the process, BDR and DR. If there's any confusion, maybe in my next video I will try to make a proper slide and explain the process. So what are the packets we discussed? We discussed hello. Now hello is critical. They need to match. A lot of parameters that need to match before a neighborship is formed. Then we have database descriptor packet. We have link state request, link state update, link state acknowledgement, right? And you know where these packets are used. Before we go ahead to the next topic, we need to talk a little bit about OSPF cost. Now, what is OSPF cost? We spoke about link state link state routing protocols. It takes into consideration of link states, link bandwidth, and all that factor we discussed, right? So there needs to be a formula. The formula OSPF uses to calculate cost is a reference bandwidth. By default, reference bandwidth is 100 Mbps divided by the link bandwidth, right? So for instance, if it's a serial connection, the speed is 1.544 Mbps. If you do the calculation, you get a cost of 64. Ethernet is a 10 Mbps line, right? If you do the calculation again, 100 by 10, you get a cost of 10. And then fast Ethernet is 100 Mbps. So if you do 100 by 100, you get a cost of 1, right? Now, what about Gigabit Ethernet? If let's say if you have Gigabit Ethernet, you have 1000 Mbps, right? But according to this calculation, it will always be 1. Right? It will always be 1. Anything more than fast Ethernet will by default be 1 cost. There's no fractions or there's no decimal points, right? So if you want to, if in your network you have a Gigabit Ethernet, you need to go change this default value. There is a provision in OSPF configurations. You can go change the default value. If you make this as the default reference bandwidth is 1000, then of course the calculation will change. Gigabit will be 1, fast Ethernet will be 10, Ethernet will be 100, and whatever that serial will be something, whatever it is, right? Now, once, let's say after we did this, we formed neighbor, we built LSDB. Now we need to build the routing table. Now how do we build the routing table? Let's assume after you got the LSDB, Link State database is ready, it's available, everything is done. Now, each of these router will have to run Dijkstra's shortest path first algorithm, right? So router A, now we're looking at this whole slide is going to be from router A's perspective, right? Router A is our hero and we are generating the routing table for router A, right? Now, let's say if it has to go to router 1, what is the cost? Of course, you know the cost is 10, right? And if you have to go to, now let's say, okay, to make it easy, let's say we are trying to go from router A to router B. Where's router B? Router B is here. Okay. We're trying to go from router A to router B. Now let's try to get all the intermediate values. So we'll check all the intermediate value for all the devices, right? So from router A to reach router 1, the cost is 10. Okay, router A to router 2, the cost is 100 because this is 100, right? We are good here. Now, from router A to go to router 3, the cost is 11. How is it 11? 10 plus 1 is 11, right? 10 plus 1 is 11. And to go to router 4, the cost, if you do 10 plus 100, it's 110. If you want to go this way, okay, if you go this way, it's 110. If you go this way, also it is 110. Perfect. So there's nothing changing. Now for router 6, if you go 100 plus 1, it's 101. That's also fine. Right? Next, to go to router 5, it is 10 plus 1, 11. 11 plus 100, 111, which is fine. To go to R7, now you have two routes. You can go like that, or you can go like this. If you go like this, 10, 110, 210. So this will be 210. If I go like this, 100, 101, 100, 201. This would be 201. Between 210 and 201, 201 is lesser, and that is why 201 is chosen. Right? Next, to reach router B, the total cost, you can go in two ways. You can go like that, or in fact, more than two ways. You can go like that, you can go like that, or you can go like that. If I'm going like this, the cost is, I think, 121. If you're going this way, 10, 100, what is that? 210, 210 and 220. So this will be 220. If you're going like this, 110, 110 plus 100, 210. This will be 210. And if you're going like this, 100, 101, 201, 211. Or what am I saying? 100, 200, 200, 211. Right, yeah, 211. Correct. So between this, 121 is the lowest, and that's why the cost of going to router B is 121, right? So this is how routing OSPF does it. So it does, in a routing table, it says for router 1, or basically it doesn't say router 1, it tells routing. This is a very simplified version of how OSPF works, but basically it would give the route network and how to go to the network. So in this case, to go to router 1, it says 10 and whatever. If this is F0/1 and this is F0/2, it would say, okay, to go to router 1, go on F0/1 and this is the call, right? So you would have all that information in the routing table using calculations similar to what we did here. All right, now we need to discuss one more topic. It's about areas, right? So normally if you configure an OSPF and if it's all of them are in a single area, right? Just think about it. It's in one OSPF area. What happens is if there is any update, like for instance, if there is a link, there's one link here and that link terminates, this device would basically start sending LSAs out saying, oh, this link is failed, and everybody would have to be updated. Now, if you are in an area where you have 1,000 routers, all the 1,000 routers will have to be updated because it's in the same area. Also, another way LSAs, let's say one of the neighbors failed, again, the same thing. All the devices in that area will have to be affected because they will have to do LSA update. Once LSA update comes, it's not only the LSA update that happens. Once an LSA changes, the topology basically changes. If that happens, SPF will have to do. So the recalculation of entire routing table has to happen again, right? So this is a big process. So if you have a lot of devices, 1,000 devices in one area, look at the size of your memory to store this LSA, right? The LSDB is going to be huge, right? Because it has to keep a lot of information for so many devices. And it has to recalculate. So every time a change happens in any part of the network, you need to do a recalculation. OSPF algorithm has to run, SPF algorithm has to run, and it's a big process. So whether link changes or if there is an update, and other than that, LSAs have a timer of 30 minutes. So every 30 minutes, so let's say router 3 generated an LSA, this LSA, every 30 minutes, it has to update itself. So if the LSA generation timer is more than 30 minutes, that particular LSA will update it. But okay, the only difference is since LSAs are generated at different times in different devices, this particular event is not going to it's not going to be a bottleneck where every device is generating LSA at the same time. It could be at different times. But again, this is something that will happen every 30 minutes for each LSA. Now that's also once that LSA updates, again, recalculation, and that's a lot of problem. One way to solve this problem, or rather this is the way to solve the problem, is by dividing your network into areas. Now as an administrator, you have to plan your OSPF, or rather your network diagram or network, the way you connect your network, such that your your area 0 is your main area, right? This is where your connection to the outside network has to happen, right? This is where, because as a rule, if you're creating new areas, one of the main rule is that all the areas should have one ABR, area border router, right? You would have one area border router. What is an area border router? Area border router is a router which has one network or one interface in one area and the other interface in area 0. Every area, like I said, has to connect to area 0. So one interface in that particular area and the other interface in area 0, right? So that's what an ABR is, area border router. Now, all the networks that's part of one area, it stays there, but one of the router, like I said, should be in area 0. Similarly, all these routers are part of area 1, and one interface of this ABR will be in area 0, and area 0 is what does connect to everything else. That's one of the critical stuff. Now, what happens now? Now, let's say this particular link goes down, or rather, there's one link connector that goes down. This sends an LSA. This LSA is affected to only area 1. Now, area 1 is the only area that has to bother about that. Like area 2 or area 0 should not even really bother about updates from area 1, because that doesn't pertain to them. Because your ABR, what it does, it summarizes, right? If you remember supernetting, it summarizes, right? So router 5 does not, because it summarizes, router 3 and other area devices need not know anything about the changes that's happening in area 1. Router 5 will handle that situation. So ABR will handle the situation at the gate, right? So this is one of the reasons why we need to do areas. And if it's confusing now, don't worry. When we start doing configuration of OSPF in our next video, and we take some examples, you will have a much better idea of what OSPF area is, right? This video was basically to give you a theoretical view of what OSPF is and how OSPF works. And when we come back to the next video, you would have a much better understanding of OSPF. So thank you so much. Please join me back in the next video, and then we'll take this OSPF journey forward. We'll see you very soon. Bye-bye.